In mid-2026, artificial intelligence reached a technical turning point. Models moved away from being passive chatbots and began acting as autonomous agents capable of executing multi-step, independent reasoning workflows. We can see the scale of this shift in the intelligence scores. Here, GPT 5.5 completes a vertical breakout past the 60-point ceiling. At this level of capability, models began solving multi-step corporate network attacks in minutes, tasks that previously required hours of human reverse engineering. This leap is the result of a shift in architecture. Developers are moving towards subquadratic sparse attention systems, which change how a model processes information. This chart shows the impact. While traditional compute costs grow exponentially as data increases, subquadratic architecture allows for flat, linear scaling. This has enabled context windows to expand to 12 million tokens, driving a 52-fold increase in enterprise compute demand. This surge in usage has ended the era of flat-rate software subscriptions. Major providers like GitHub have transitioned to metered, usage-based billing to manage the costs of these continuous agentic workflows. But these virtual gains rely on a tangible foundation. Every token generated by these models requires a measurable unit of physical hardware execution. To build that foundation, hyperscalers have increased their capital spending to over $700 billion. We are now seeing the construction of gigawatt-scale data centers designed to house over 500,000 GPUs in a single facility. This chart shows the problem. U.S. generating capacity is dwarfed by 1.84 carawatts of new interconnection requests. Demand officially exceeds supply. Converting this to a timeline reveals a mismatch. 2-year data center builds now face a 7-year grid connection queue. The grid is buckling under the weight. In early 2026, the Department of Energy shifted data centers onto backup power to prevent residential blackouts. Meanwhile, massive 9-gigawatt projects are facing local resistance as they threaten to consume more power than the entire state of Utah. The rapid growth of AI has crashed into the rigid limits of the electrical grid, creating a zero-sum battle for the legacy power supply. Even if the power is available, operators face the laws of thermodynamics. Modern AI server racks now draw up to 120 kilowatts of power, concentrating an immense amount of heat into a very small area. Traditional air cooling is no longer effective at this scale. When rack density reaches these levels, the rapid heat generation surpasses physical limits. Fans and HVAC systems cannot move air fast enough to cool these next-generation chips. This has forced a reliance on evaporative cooling, with some facilities consuming 5 million gallons of fresh water every day. As water scarcity becomes a local regulatory priority, the industry is finding it impossible to scale using these legacy methods. To continue growing, the AI industry is being forced to abandon terrestrial infrastructure norms and engineer entirely new ways to generate power and reject heat. Hyperscalers are now moving behind the meter. To bypass the 7-year wait for grid access, tech companies are building their own self-generating power hubs directly on site. The immediate solution involves natural gas fuel cells. These provide direct current power to the servers, which eliminates the need for the massive, custom-engineered AC transformers that are currently backordered across the industry. For long-term baseload energy, hyperscale companies are turning to small modular reactors. These modular nuclear plants are designed to be deployed directly on a data center campus, providing a localized, carbon-free power source. But even nuclear power has a bottleneck. These reactors require high-assay low-enriched uranium, or HALEU. Currently, there is only one company in the U.S. licensed to produce this fuel at a commercial scale, creating a single point of failure for the entire strategy. To solve the cooling crisis, engineers are adopting 2-phase thermosiphon systems. This technology uses a closed-loop coolant that evaporates and condenses to reject heat, achieving high efficiency without consuming a single gallon of water. The trillion-dollar race for AI has transformed into a heavy industry race to build parallel energy and thermal infrastructure that operates independently of the public grid. The ultimate solution to these terrestrial limits involves leaving the planet entirely. By moving compute into space, developers can bypass land, water, and grid restrictions. This is the goal of Google's Project Suncatcher. The plan is to network a constellation of solar-powered satellites in low Earth orbit, using optical lasers to transmit data between orbital server nodes. Anthropic has taken a similar path. partnering with SpaceX to secure terrestrial superclusters, while co-developing the specialized hardware needed for orbital AI processing. Operating in a vacuum requires a complete redesign of thermal management. Without air for convection, these satellites must use massive, deployable radiator sails to bleed off the heat generated by the processors through pure radiation. Scaling artificial intelligence has evolved into a massive engineering project, moving from terrestrial power hubs to a new generation of orbital compute platforms.